Section 2.8 is linear approximations and differentials. So we've already talked about finding the equation of a line tangent to a curve by finding the slope of that line with the derivative of the function f prime of x or f prime of a specific value a. And we're going to extend this notion into an approximation. So when we say a linear approximation, we're going to use a tangent line to a given curve in order to approximate values on that curve. So in this case, we're given a function y equals f of x. That's this curve in black ink here. And then we've got a tangent line. It's the one given in red here. And you notice that, at its simplest, this idea seems to make sense. If we want to estimate the value of the curve f of x for some x value that's near this a value down here on the x-axis, so in other words, we want to guess what this x value is to the right of a, we wouldn't be too far off to use this line, right? The point on the line above the point on the x-axis down here is not too far from the actual point on the curve. Now notice though that the accuracy of this linear approximation starts to degrade as we get further away. Over here, the point on the curve is that much further away from the point on the tangent line. And then it just gets worse and worse as we get further away. Same thing over here, probably over here, something like this. We'd be missing by quite a bit. So the whole notion of this is the following. This is what's going to be the theme for the entire section, is that the closer we are to the value that we build our linear approximation or form our equation, our tangent line, the more accurately we'll be able to approximate a function's value at a specific x value. So let's get back to something. Let's come back up here, and we're going to take a function f of x, which is differentiable at some number a, so x equals a, and we can plug in a to get the y value at a, which is f of a. Again, this is all marked off down here in the picture. And in order to find the equation of such a line, we just have to remember this. Well, the slope of the tangent line is f prime of a, right? So what this equation right here is really telling me is I've got y is equal to m times x minus, well, a could be, I'll just leave it as a, I suppose, or x naught plus, this could be y naught, but we have it as f of a, but we just know that that's the y value and the coordinate. So this is the equation of the line tangent to the curve y equals f of x at the point a, f of a. Okay, so there's our full piece of it. And instead of just putting an m here, we know that that is explicitly the derivative of f at the number a. So this is our sort of governing equation here for finding the equation of a line tangent to a curve, the x value, x equals a. And we'll always end up, you can always use that to find that equation of the line. So notice this does come from point slope form. This would be y minus f of a or y minus y naught. And that gives us that left-hand side just by moving over this term right here. We'd have exactly point slope form. Okay, so we're going to leave it in this form because this is the more useful scenario for us, because what we're going to do first is we're going to talk about this as a linear approximation. So if we have an x value that's close to a, like I said in the picture down here, so if we pick an x value, say like here, well, we're going to get a reasonable approximation for x's value by using its value on the line. And it's easier to calculate the value of x on the line in a lot of cases because f might be a more complicated function than the equation of its tangent line. So that's the whole point of this. And we'll see this, we use this to approximate root values and values of other trickier functions like trig functions maybe. So that's really the essence of a linear approximation, right? We can set up, we'll call this line L of x is our linear approximation of the curve y equals f of x, and it'll be at a value a. And that's how we'll construct it each time. So notice that if we're interested in finding the value of the curve at another x value that's near a, then it's going to be approximately equal to this line, the value that this line puts out, right? So that's The distance that we see between the red line and the black curve is the error between the two, and that's the error in our approximation. So there's the setup. I think the execution of this at first is pretty easy, to find the linear approximation of a function and then approximate with it. Here it is named for us, as we see here. And just note the difference. L of x, that's the line tangent to the function y equals f of x at the value a, right? We might sometimes put L sub a here. You might see something like that happen. So I'll write that in. You might see a script L sub a. And that's saying, and that a would be a number, L sub 2, the approximation, the linear approximation at 2 as a function of x, right? And then this would be a 2 in all cases. And we figure out what those values should be and have them appropriately in the equation. We note that the value of the function itself is approximately equal to this linear approximation. In other words, the curve is pretty close to the line as long as x is close to the value a. Okay, so let's actually use this. This first example says find the linearization function of f of x equals root x at a equals 9. Can use it to approximate the number root 8.9. Okay, so at the start, we kind of see the setup of it all, right? And this isn't anything necessary to do before you start one of these problems, but you can see what the goal is, right? We're going to build a linear approximation at a equals 9 for this root function, square root of x. Well, that's a very reasonable place to do a number to use. One, because 9 is pretty close to 8.9. So if we want to take the square root of 8.9, we can use a value that's easy to take the square root of, like 9, and is close to 8.9. Because of course, in this formula, we're going to have to find f of a at some point. So we're going to have to plug in 9 to this equation, and we'll get, well, of course, we'll get a 3 out. So we see the setup for this. So if we want to approximate the square root of something, whatever it is, we might pick the nearest number that's a perfect square, build a linearization function like this, L of x, and basically follow the procedure that happens below. So the first thing we need to do is we need to build this L of x equation. So let's get into that. F of x is x to the 1/2. That's our square root of x function. So we take its derivative, f prime of x, by the power rule is 1/2 x to the negative 1/2. We're going to need f prime of a for our linearization. So we're going to do f prime of 9, and that's going to be 1/2 times 9 to the negative 1/2, based on that formula or that rule for the derivative. And that comes out to 1/6 when we're done with that. Right? Remember, the negative power takes the reciprocal of the number, so we have 1/6 here. And we're going to need f of a, right? And that's why we chose 9, because it's close to 8.9, and also it's a perfect square. It's easy to evaluate. The square root of 9 is 3. So we've got all the pieces now. We have a is equal to 9, so that'll be a 9 right here. We have f prime of a is 1/6, and we have f of a is 3. So we have all the pieces we need. Notice that x is just going to be x, right? This is a function of x. This is a linear function of x. So we put it all together. Here's what it looks like. A is 9, of course. We plug all these numbers in, as I said. We have 3 plus 1/6 times x minus 9. We could simplify that, but this is a perfectly reasonable approximation tool. Okay, this is our L of x, our linearization function, or our linear approximation. So if we want to know what the square root of 8.9 is, well, it's the function f of 8.9, right? That's what the function tells us to do, take the square root of something. So that function is somewhat, or reasonably approximately equal to the linearization function at that value. So in other words, the curve itself is roughly equal to the value on the tangent line. And that's really all we need to do. We just need to plug in 8.9 into this linear approximation rule. And it looks like this, 3 plus, well, this is going to be an 8.9 that goes right here. We have 8.9 minus 9, that's going to be negative 0.1. So that's that operation there. And then we've got 1/6 times negative 0.1, and we just kind of have to wrap up the details here, and this comes out to 179 over 60. So it looks like f of 8.9, which is also the square root of, or sorry, the square root of 8.9, looks like it is approximately equal to 179 over 60. Now that's an easier process than trying to do some kind of iterative root calculation. If you ever learned how to do that by hand, we're able to come out with a reasonably accurate approximation simply by using this linearization, knowing the derivative. And this is, in fact, is well, a method somewhat similar to this. Iterative approximations via Newton's method are how square roots are actually calculated by a calculator when you get a decimal approximation of something. In our case, we've still got a long ways to go before we get there, but we will see that. This is reasonable enough as long as this number is close enough to the actual value, a equals 9. And the further we get away from that linearization value, the value at which we form the linearization, the less accurate our approximation will be. So the next question asks, is this approximation an overestimate or an underestimate? Well, the easiest way to answer that is to just have a look at the curve y equals square root of x. I guess another way to do it would be to write this number down, right? Or maybe calculate what it is as a decimal, and then plug this square root of 8.9 into a calculator, and then you could compare. But there's not really much insight in that. You don't learn much by doing that, but you could also, you can confirm what my claim is going to be here. And that might be valuable. So here's the linearization, that line right here, of the curve y equals root x at the a value of 9. Right? This is the equation of the line that we came up with for linear approximations. And as we can see, if this is an accurate enough representation of y equals square root of x, the function we're dealing with, and this line, 3 plus 1, 6 times x minus 9, then we can see that this is the gap between this line and this curve is pretty small, which that means the error is not too egregious, right? It's a pretty small error, and this linear approximation does a good job of approximating values, square root values out of this function. So 8.9 would be a little bit to the left, and it would be a little bit off to the side here from the value of 3 on the y-axis. It looks like, if we look closely, and it's kind of hard to see it because it's hard to draw it perfectly, but we realize that the line tangent to the curve is above the curve itself. And the value that we came out with was the value from the line. So again, it's not really drawn very well, but the red curve should really be above it by just a little bit, something like that. So we can see from this tangent line that this must be an overestimate because the values on the line are a little bit above the values on the curve itself. So this would be an overestimate based on that. If you were to graph both of these in Desmos or a nice graphing calculator, this function and this function, you could see more clearly that this is actually the case, right? That there's this little gap here. And that's really about all there is to it. Sometimes you'll get a problem that'll say, approximate this root. Use linear approximation to calculate the square root of 8.9. And they won't give you the rest of the problem. So the pieces you need to put together is this. There's a function at work here, and that's the root function. So then you're going to write down f of x equals root x, and you're going to want to find the linear approximation of that. And then you're going to want to find the number that's closest to this value of 8.9, but is a perfect square. In other words, is very easy to evaluate this function for. And in that case, you would 0 and find 9. Okay, maybe some guesswork would help. Or would be required, but nonetheless, it wouldn't be too hard to find that. And we'll do a problem somewhat similar to that before we're done with these notes. Okay, so yet another one. Find the linear approximation of the function f of x equals tangent x at a equals 0. Okay, so again, they're not being too roundabout with the problems to start. They just tell us what function we need a linear approximation of, and they also tell us where we want that linear approximation to be centered. Okay, this is where it's centered, is the value that we're given. So same formula, and we're going to need f prime of our function f of x here, and we're going to need to evaluate it a equals 0. So f of x is tangent x, so the derivative of f is secant squared x. So maybe a reminder, looking that up in the book if you need to. And then we've got f of 0, that's plugging in 0 for x. Well, tangent of 0 is 0. And then f prime of 0, that's secant squared of 0. Well, secant squared of 0 is 1. Remember, secant squared of x is 1 over cosine squared x. Cosine squared of 0 is 1 squared. 1 over that is 1. You can check that with on your own. So L of x then is f of 0, so our a value is 0, right? Plus f prime is 0 times x minus 0. Well, f of 0 was 0, so that's easy. And then f prime of 0 was 1, as we found off to the right there. So we plug that in, we have times x minus 0. Well, all of this just simplifies to the linear approximation L of x equals x. So that was quite nice, just thanks to a bunch of zeros showing up in there. And if you were to graph y equals tangent of x and y equals x in the same graph, and I advise maybe you try to do that, you'll see that these are reasonable linear approximations. Here's what tangent looks like. This is its principal cycle, the one that passes through the origin. Remember that y equals x looks something like this. So it's tangent to the curve right here. And it's a weird one because the point of tangency is an inflection point, so it looks like it just crosses through it. But nonetheless, you could see that this line is a reasonable approximation for this blue curve, y equals tangent of x. So as long as we're close to 0, somewhere in here, we can use this line to approximate values of tangent of x, as long as those values are close to 0. So, or our center of our linear approximation. I guess now the other question that we could ask those, well, how do we know the accuracy of such an approximation? So in other words, let's look at question B here. It says, for what values of x is this linear approximation accurate to within 0.1? Okay, so in other words, our error is no more than 0.1. So our approximation is off by no further than 0.1. This requires a graphing tool. I think this is probably best done with a graphing tool. Otherwise, we have to solve an equation like this, and that really takes another method of approximation that we'll learn later on. So what we're asking is this: when is the function itself no different from the linearization by 0.1? So you can always write that as absolute value. The absolute difference between f of x and its linear approximation needs to be less than 0.1. Well, f of x is tangent of x. Here's that part. And then L of x is x, as we found above. So really just asking for what x values, what interval is tangent of x minus x less than 0.1. And there's some symmetry here, right? So we can actually, if I need to break this up, what I can do is this. I can say, remember the absolute value less than is written like this. Let's say tangent x minus x less than positive 0.1. So that's my interval that I'm looking for. So the best way to do this, or an easy way to do it, rather than try to graph each of these and look at them on a graph somewhere and try to see what the distance is between them, you can just graph the function that we have right here, tangent x minus x, this function here, and then just see where, approximately where its y value hits negative 0.1 and where its y value hits approximately 0.1. And of course, you can see that there's probably going to be some kind of symmetry thanks to the symmetry of both of these curves and the point at which they're intersecting each other. And you can exploit that in your answer. So let's go ahead and have a look at this. We'll go over to Desmos to do that. And let's see if I can find that quickly. Calculator, or graphing calculator here. So we're going to have y equals tangent of x. So we need to find in our functions menu tangent. There it is, tangent of x minus x. Right, we just put them both together. And now we can zoom in on our primary point of interest, right? So we're here. is where we're really interested, right here at the origin. And remember, I put the difference of my two functions as the difference of the function itself and the linearization. And what I'm really interested in is where are the y values that make this curve, or where are the x values that make the y values less than 0.1. So maybe I touch a point here on the curve. I see 0.77 and then comma 0.2. That's too big. My error is now too large. So I'm going to scroll down a little, and I'll go to, it's like 0.69 has me a 0.135. So I'm watching that y value, and I want it to be less than 0.1. I could just ease it, maybe. So it looks like it's about 0.63, right? Just about yeah, so we'll just round that to 0.63. So as long as our x value is between 0 and 0.63, then we know that from the origin to about here, about here, that we're going to be within our error tolerance. We won't have an error of more than 0.1. Now that should be the same on the other side thanks to the symmetry of this curve, right? And I can kind of scroll this way, and now I want that y value to be greater than negative 0.1, right? That left-hand side of the interval. And as I scroll down, yeah, it's about negative 0.63, right? If I come back, so we're just going to go with negative 0.63 to positive 0.63. And there it is. Remember, all we graphed was the difference of our actual function, tangent of x, minus its linearization that we're using. And then we just look for the y values that are less than 0.1 and greater than negative 0.1. So that's really all there is to it. Notice that this is different from the graph of y equals tangent of x, right? We could have done this way. We could have graphed y equals tangent x, and then we could graph y equals x. But we're a little bit more out of luck with this tool if we do that. We have to figure out a way to measure between the red curve and the blue curve in these zones, right? And I think we remember that it was about 0.63 if I can get a point on this curve. Here we go. And yeah, then we just have to know what the distance between the red line and the blue line are. That doesn't really tell us the distance there. So that's why we chose to write tangent of x minus x. And we can then find it by just bounding the value of that function. In other words, bounding our error function. Okay, so to get back to our linear approximation, we can write down the interval that keeps us within the error tolerance of 0.1 is going to be negative 0.63 to positive 0.63. Okay, and that's what we actually have written down here. Okay, so that's a nice way to handle that sort of problem. Okay, so linearizations, in other words, the equation of a line tangent to a curve at a given point, and using that to approximate values on the curve itself that are near the linearization point, is a pretty straightforward concept, but it's connected to this idea of a differential. Okay, so all along, we've talked about this idea, this derivative dy dx being equal to f prime of x. Okay, what's happened here in this box is we started to treat dy dx as though it's this separable ratio, right? So we can write dy as f prime of x times dx. Well, each of these pieces, dx and dy, are called differentials, right? So we've talked about this before in other problems, particularly related rates. We talked about the change in y over the change in x, or delta y over delta x, things like that. And these have been sort of vaguely hinted at all along. Now we're going to make that a little bit more formal. Okay, so x is an independent variable. So dx, the differential dx, is going to be an independent variable as well. Okay, and we'll do more with that in just a moment. So dy is a dependent variable. Y is a dependent variable. And so dy is going to depend on the change in dx. So our change in our y variable, the change in y is equal to the derivative of f at x times the change in x. Okay? We're going to build a whole new approximation formula out of this. Now, we need a definition. Delta pretty much always stands for a difference. Okay, so delta x is a change in x. And what we're going to end up doing is calling delta x dx. Since they're both independent variables, we can just assign them to be equal to each other. And that's what you see down below. We'll do that formally in just a moment. But for now, the change in y, if we were to look at the graph of this function, and we'll do that down below in a moment, it's equal to f evaluated at x plus delta x, and then minus f of x. This is where f was to where f ends up. Okay, so let's look at that down in the picture below in the graph. So delta y right here is the change. So maybe if this is our curve, y equals f of x here, okay, some arbitrary curve, then f of x is this point, and then f of x plus dx, or delta x, we've assigned these two to be the same because they're just independent variables, just like x is. So x can change all it likes, however much that changes, well, that's what delta x or dx are equal to. Okay, so we move from x to dx, or to delta x, x plus delta x. And when we do that, it's going to change our y value from f of x up to f of x plus dx, or f of x plus delta x. So it's going to move from here to here. So there's our difference in our y variable, or y values, is it's the distance between this value and this one. And that's exactly what this is telling us here. So that is our change in the y variable, is what we'll call that, change in y. And well, if we look at this in another light, if we think about dy, well, dy was defined as f prime of x dx. Well, that's based on the derivative. And what that's going to capture is this. It's going to say, okay, sure, we started down here at a y value of f of x. Well, by the time I get to this x plus dx, or x plus delta x, x value, the linearization, which dy is based on the linearization, right? It's based on the derivative, or the tangent line of this function. Well, dy is the value between L of x and f of x. Okay, so we'll put these pieces together even more. We're going to expand what L of x is from what we used previously and derive a new formula for all of this. So it turns out, as long as we're pretty close to this x value, and that's a relative thing, right, then delta y is pretty close to dy in value. So we kind of see that dy is approximately delta y. So let's do the finishing moves on this derivation. So we've got this approximation here. Delta y is approximately dy. Okay, so long as dx is sufficiently small. In other words, we don't move too far away from that x value we centered at. So what we need to do is call dx x minus a, right? In other words, if we're centered at an approximation of a linearization of a somewhere, or a value of a on our curve that we'll plug in, then d of x is, well, some new distance away from a. And that, if we solve for x in that case, we have x is equal to a plus delta x. So this is just introducing our centered approximation at a, and then x is a value we might be interested in calculating the function at. Okay, so f of a plus dx is f of x, right, based on this equation. And then we've got that that's approximately equal to f of a plus dy. Well, that's because dy is f prime of a times x minus a, right? And that is all from our linearization function, right? dy, based on an a here, y, f prime of a times, delta x, right? So in dx, we see is x minus a, right? And that was So there's our slope, and part of our point slope form. The rest of that is plus f of a, and that comes from here. So this is what we're able to do. We're able to use differentials now to approximate functions values of functions near friendly values like a. So okay, that's probably it's a tricky derivation to sort of wrap your head around. It's a odd extension of variables, but you should track the details out if you're interested in that. Later, I think what you should do first is learn how to do these problems, get a feel for them, and then you can go back and kind of hash these details out again to get a deeper understanding of it if you like. I don't think it's absolutely necessary to have the full understanding, but to see that derivation is nice, and to have that understanding is always, it can't hurt. So we're asked to rewrite the linearization function of f of x equals root x at a equals 9 in terms of differentials. So what we're going to do is we're going to compare this new method to what we did in the old method. So instead of writing down the function L of x, our linear approximation function, what we do in these situations is we look at the problem this way. A is going to be 9 here, and then we're going to say how far away from 9 are we going to deviate? And if we know how far away from 9 we deviate, then we can calculate approximately what the value of that function is by knowing its value at 9 plus dy, right? So let's see all these things. So they're asking us to determine dy, then f of a plus dx for this approximation. So f of x is root x, that's x to the 1/2. Derivative of that is 1/2 x to the negative 1/2. Okay, f of a, we're going to need f of a in our formula. So that's f of 9. F of 9 is just the square root of 9, so that's 3. We've got that laid out there. Now, the left-hand side of this, a is 9, so this is f of 9 plus dx. We're building a general differential approximation formula. So we know that a is 9, that's the center of our approximation. Dx is going to be whatever deviation we like, whatever number we want to find the value that's near 9. Well, dx is the difference of 9 in that number. Get there in just a moment. Now this is approximately equal to the function evaluated at 9 plus dy. Remember what dy is from the previous page. Dy is f prime of x dx. Well, okay, f prime of x is the derivative of x here, or of f. So we can write that down. So dy is written as this differential expression, 1/2 x to the negative 1/2 dx. Okay, remember this is all proportional. So this is all proportional to what happens. How far away from our a value we get is what dy is going to be, right? What our output is going to be. So a equals 9. Plug that in for our dy differential approximation right here. 9 to the negative 1/2. Well, this is a familiar number, and it should be. A lot of these parts are very similar to the linear approximation formula technique. And we have dy is equal to 1/6 dx. Okay, this will always work out to a nice, we're always going to plug a number into this function, this derivative here, right? So we're always going to have this sort of linear step scenario that's going on, this 1/6 constant times dx. So you'll always have a constant times the differential dx for one of these approximations. So it's very much like a linear approximation. It's just thinking, instead of having the x be the variable, you're having the step away from the ideal number like 9. Dx is actually the variable. So we have our differential expression for this function. F of 9 plus dx is approximately 3 plus dy. Well, dy was 1/6 dx. Now, anything we want to find the square root of or approximate the square root of based on this differential equation, or I guess it's not a differential equation, but this equation of differentials, we can find the difference between 9 and that number and write that in as dx. So in other words, if I want to find the square root of 8.9, in other words, the function of 8.9, Well, then I rewrite it as the difference of 9 minus 0.1, right? Because my idea is to construct this as I need a 9 right here, so I need to match that 9 in this decomposition of this number. In other words, what I could do is just take 9 minus whatever this number here is, and then I'll write that as 9 minus that here. Okay, so we split it as follows. We know that dx is 0.1. That's the whole point of that. To find dx, you do the a value minus the value that you're interested in approximating at. So this is 9 minus 0.1, and that allows us to write the argument as the right-hand side of the differential here of this equation or approximation. So we have 3 plus 1/6 times negative 0.1. When we work all of that out, we end up with 179 over 60. And that should look familiar if we go back a couple pages. 179 over 60 was what we got as the approximation here. So these are one and the same types of methods. The difference is that here we think of the x variable that we're interested in approximating as being the variable itself, whereas in the differential situation, we're thinking about the variable being the difference away from the ideal value that we are. In other words, dx. That's our variable in this. Okay, so let's do a couple more of that because this is a kind of an odd concept. So use differentials to estimate the cube root of 1001. Okay, so they're leaving us a little bit more in the dark than they have with other problems, right? So in other words, they're not giving us a function to use. Well, it should be pretty obvious what function's taking place. We're going to estimate the cube root of something. So f of x is probably the cube root of x, right? That would be a good decision to make, right? Now, what's our a value? Well, the a value we need to think of is a number that's a perfect cube that's close to 1001. And a lot of times it should be fairly obvious, like this case. Well, 10 cubed is 1000. So a should be 1000 because it's easy to find the cube root of 1000, something we already know. And that's going to be the center of our approximation. A will be 1000 because f of a, of course, is 10. Okay, now they want us to use differentials to estimate this value. Well, the rule for that looks like this. F of a plus dx is approximately f of a plus dy. Could go a little further and write down what dy is. dy is f prime of a dx for a given a value, just as we did before. So again, maybe if we didn't, so I started here to identify parts, but it's okay. We could have said, okay, we need differentials to estimate this. So I need something that looks like this. So then I need to know what a is, and I need to know what dx is eventually, and I need to know what f is. We've got most of those things already. Notice we're going to need the derivative of f now that we've settled on what the function is. Well, that's x to the 1/3. Its derivative is 1/3 x to the negative 2/3. So we're ready to use that. Now we should evaluate f prime at a, right? Well, a is 1000. F prime of 1000 is just a matter of plugging 1000 into that expression, as we've done over here. And that comes out to, it looks like 1/300, the value that comes out here. So that's nice. Again, I told us on the previous page that that's a constant each time. Last time it was 1/6, and this problem it's 1/300, and that's always going to be the case. It's always going to be a constant, and that's going to make our calculation or our approximation pretty easy to execute. What else do we need? Well, we have f of a, that's 10, right? And these are essentially all the pieces then, right? So we can write down our differential. It looks like the following. F of a plus dx is approximately f of 1000 plus f prime of 1000 dx. That's essentially filling in a equals 1000 for all these pieces. Now we have all the numbers that we need already calculated for this. So this comes out to f of 1000 plus dx is 10, it's this value, plus 1/300, that's this value, dx. So now if we want to approximate the cube root of something that happens to be near 1000, well, we can just find the difference, dx, between 1000 and that number. Okay, well, the difference between 1000 and this number or 1001 minus 1000 is going to be 1, right? Difference between these two is 1. So we're going to step by 1 unit to the side. So what we want to do is we want to write f of 1001 as the decomposition of 1000, our sort of special number, plus however many it takes to get to this other value. In this case, it's 1. The difference of this one minus that one. So once we've got this, we know that dx is 1. So we know what to do on the right-hand side of this. So we have that the cube root of 1001, or f of 1001, is approximately equal to 10 plus 1 over 300 times dx. Well, dx is 1, so 1 over 300 times 1. When we get a common denominator for all of this, what we end up with is 3000 plus 1 over 3000. So that's 3001 over 300. So we can conclude that the cube root of 1001 is approximately 3001 over 300. Now, the nice thing is we've got a calculator, and we could just plug in cube root of 1001, see that as a decimal approximation. We could do the same for this ratio, this fraction 3001 over 300, and you should find that I think each of these is about 10.0033 or something like that. But you find that they're rather close. So we did a pretty good job of approximating this root. So there we have it. Notice again, how do I find dx? Let me be more clear about that. Dx, we have to recall, I'll put that down at the bottom here. Dx on a previous page was x minus a. So in our case, dx is x minus 1000 here. And the x value that we end up being interested in is 1001. So dx in our case, when x is 1001, then dx is equal to 1001 minus 1000. And that came out to 1. And to show that more explicitly in the previous problem, I'll do it again down here. dx is x minus a. In our case, the special value a was 9, and 8.9 was the value we wanted to approximate at. And this came out to negative 0.1. And that's, of course, what we used. I don't have that written here correctly, but it was input into the formula correctly. dx is negative 0.1 in this case, okay, as we see it right here. We calculated correctly that I just labeled it wrong right here. So that's how you'll find that. It's the x minus the special value a, or the center of our approximation a. Okay, so for one more, they'll ask us to find the let y equals tangent of x. We've already seen this one before. Find the differential dy. So we're just going to do the same approximation we did before, but this one again with a differential rather than a linear approximation. So dy equals f prime of x dx, as always. In this case, they're actually asking us to do something more specific and smaller. They're saying just find the differential dy. So if we have a problem that asks us to do that, we just remember that dy is f prime of x dx. And there's no a value here, right? So we're not asking for an a value, some special number or anything like that. We're just going to find the differential dy. Well, that is literally a matter of taking the derivative of f of x equals tangent x and getting f prime of x equals secant squared x, and then plugging that into this formula. So dy is equal to secant squared x dx. So that's our differential dy. Now it's just like a moving piece here, right? This little formula tells me that if I change my x value by a certain amount, it's going to change my y value by a certain amount, and this function is going to be part of that process. Okay, it's going to affect our y value. So nonetheless, that's a bit more abstract than the matter at hand. So part B says to evaluate dy and delta y if x is equal to pi over 4 and dx is negative 0.1. So now we're given all these nice little pieces that we can start to plug things into. Well, we have to remember what each of these is. There's dy, there's delta y. Now they're giving us a value of interest. X is pi over 4, and really this is sort of our special value, right? An a value of pi over 4 that we're interested in. We're going to center on this value, and we're going to change by negative 0.1. our dx, our change in x, is going to be negative 0.1. So on the for the differential side of things, it looks like the following. Well, we'll write down each of these. dy is this differential, and delta y is this difference, right? We've had this on a previous page too. You can look that up a few pages earlier than this to see what that where that came from. That was our definition for delta y, or change in y, or the difference in y. So dy is f prime of pi over 4. That's our special value, right? Our value of interest. And then that's times dx, which is negative 1, our differential. It's just what this formula tells us to do. Well, what is, now we're just really employing the formula up here. Dx is negative 0.1 in that formula, and f prime of pi over 4 is going to be secant squared of pi over 4. So that's what we have going on right here. Secant squared of pi over 4 times negative 0.1. Well, it turns out secant squared of pi over 4 is 1 over cosine squared of pi over 4, if that helps. But it just turns out secant of pi over 4 is root 2. We're squaring secant's output, so we're squaring root 2 times negative 0.1. So dy is negative 0.2. That's pretty easy to calculate. The change in the y value is that much if we deviate from x equals pi over 4 by negative 0.1. Okay, on the other hand, the difference in y is maybe a little bit harder to calculate, and we'll see why in a moment. The difference in y is, we'll take our special x value, perturb it, or move away from it by dx, and then subtract from that value f of x. Well, f of pi over 4 won't be hard. That's the tangent of pi over 4. And then f of pi over 4 minus 0.1, well, that one's harder. That's tangent of pi over 4 minus 0.1. This value we can calculate. It's 1. The other value, we don't know, right? We could get a calculator to help give us an approximation for that, but we just don't know it. So not off the top of our head, it's not a special value or anything. So we just write it as tangent pi over 4 minus 0.1. Now what's interesting then, and you can confirm this, we know that dy, so long as dx is not very large and negative 0.1 is relatively small, we know that dy is is approximately equal to delta y. And so you could check, is negative 0.2 approximately equal to tangent of pi over 4 minus 0.1, all of that minus 1. And you should find that they are relatively close in value. Maybe not exact, probably not exact, but close enough. And the smaller this differential is, the smaller, or the more accurate this approximation here will be. So one last example, I won't go through all the details of it, but these notes will be posted and available in the annotated lectures folder, of course, so you could look through it if you needed to. This problem says use linearization, in other words, L of x of f of x, then differentials to approximate the square root of 38. So it's yet one more value, one more round of practice here. You can immediately recognize the function as square root, f of x equals square root x. And then you want to pick a value that's close to 38 that's a perfect square. Well, some trial and error, you might say 5 squared is 25, 6 squared is 36, 7 squared is 49. Well, 36 was the closest in that list, so 6 squared, 36, a equals 36 should be our sort of special value, the center of our approximation. So you're going to want to take a to be 36 in all of this, and the rest of it is just the method of finding the derivative. F of x equals root x, and evaluating root 36 and x minus 36, and all these values coming together here. Similarly, you can do the same for the differential. Again, a is going to be 36, and the function f is going to be the square root of x, and then you just have to find dx by doing x minus a, or x minus 36, or 38 minus 36. All that's done down below. You can find these notes to work through it. But notice the problem is asked in this form, right? And then you've got to kind of figure out what a value you're going to need to use, as well as which function is appropriate. So that should be somewhat obvious in most cases. There we go. That's it for differentials and linear approximations.